Okay, today I will show where these Cauchy-Riemann equations are coming from. As you may already know, these equations are very useful to when we want to verify if a function is not analytics. Remember that to be analytic, it will require a few extra things. I mean, the Cauchy-Riemann equation is one of these things. The other things are to have derivatives in a specific region for these functions, and also that it will be continuous. So, but if we just want to show that it is not an analytic, this could be an easy way to do it. So, where are these coming from? Let's start with the proof. So, as we know, we can add a function here, which is a complex function, so that if we derive it in a specific region D, this delta C will tend to be 0, but it will tend to be 0 for many places. I mean, it's not just one dimension as we did in the real line. Now we can do from the real line, but also from the imaginary dimension. So let's approach it right now from the real dimension. How it will be. So if we just take this part, the part of inside of the limit, which is the definition of the difference when delta C tends to be 0. How it will be if this one will tend to be 0 from C. So we have to change everything in the top, and we remember that we have u as a function for the real part and v as a function from the imaginary part. So we set it up this part. The first set will increase in the x-axis but not in the y-axis. The same thing from the imaginary part here. This one will be the same. If we separated this in two different sets, we will have this difference that looks like the initial one, but this is just for u and this is just for v. So if we pass this to the limits as we have here, and there is a theorem that said that we can distribute the limit whenever the limit exists, then we will have basically the partial derivative of u and the partial derivative of v. Of course, whenever c is an x plus iy. Because this is a continuous function, also the derivative, the partial derivative, will be continuous too. Okay? Let's continue with the proof. So next, let's do exactly the same thing, but in this time we will approach 0 from the imaginary dimension. Again, we do this increase of the delta y in the y side of the u function, the same thing from the v function. Then we redistributed this across the numerator, and then separated, and we will have this difference. If we pass this to the limits again, we will see that this satisfies the functions as in the previous equation, but now with the partial derivative on y from v, on y on u from y. Again, when c is split as a real and imaginary part. So the equations, if we see, basically we will have the same, that the partial derivative of y will correspond to the partial derivative of u through x and same thing for the other side. So that is basically where it's coming from, this equation. These are the Cauchy-Riemann equation. Now, as I mentioned it, if we want to show that a function is analytic, we need a little bit more of just the equation. So for that part, we will approach this from a different perspective. Let's fix C in some part of the domain D, and then let's use the Taylor expansion. If we use the Taylor expansion for U, right, where U is this x with the addition of the delta x and y is the y with the addition of delta y, we will have basically this part, right? The initial one that doesn't have the derivative, the partial derivatives, and the remainder. The remainder will be also a function on the deltas, right? These deltas will tend to be 0 here, as we see, right? So the continuity of the first order partial derivative of u must be obtained for estimated the remainder, right? Similarly, we can do this from using the function v. We obtain the Taylor expansion. We have another error function here, which is tending to be 0 as the delta c tends to be 0. If we combine these functions, the one that we have previously plus this one, we will have all the approximation from z to be 0, right? Not just the one from x and the one from y. So we will have these derivatives that we have plus the error functions. If we use the Cauchy-Riemann equation to replace the y derivatives by the x derivative, and we use the delta x plus I delta y as a delta c, then we will have this new function, right? Basically, we are just changing, using the Cauchy-Riemann equation to do this change, and then we will have basically these new equations that will have the delta c as a multiplier. Then if we simplify this, if we move this to the other side, and so we will have, of course, this is tending to be 0, okay, this part. So we will have that the derivative, the partial derivative for both of the sides will correspond to the derivative function that we have at the beginning, plus the error function, which tends to be 0. So this, because this trying to become 0, we will have only this function, the derivative, the partial derivative for each of the sides. So therefore, the derivative of the complex function exists and it's continuous, and of course the function will be analytic. Okay, then we can basically formulate a new theorem here, which is this one. If the function, which is in a complex plane, will be defined in a domain D, is complex plane in the complex planes where u and v are the real values, then the function in C is analytic on D if and only if u and v, the function u and the function v, have a continuous first order partial derivative that satisfies the Cauchy-Riemann equation. So we need the Cauchy-Riemann equation plus the continuous first order partial derivative, and we define it in a domain, a specified domain, to be analytics. Okay, I hope you guys enjoyed